Hey guys, so this is the video for physics for 23.1 through 23.3. I'm going to go over a few different things, some calculations, and some things that we can kind of understand about understanding how light works off of mirrors for the day. So today we're focused on mirrors. I know you guys have all had experience with mirrors, but hopefully you've also recognized that not every mirror is a flat mirror like the one you'd see in your bathroom. Everything from compacts, which women used to carry in their purses all the time. Don't know if that still exists. I think it does. But to the mirrors in your car, telescopes, a lot of things. We don't use just flat mirrors anymore. We use a lot of different kinds of mirrors, and they have curvature to them. So we're going to talk a little bit about that. We're going to use this idea of a ray diagram for mirrors and also for lenses. Think of it as if we follow a ray of light, okay, and assume it travels in a straight line, then we can use mirrors to do reflections and bending of light. So a really common example, we're going to talk about these plane mirrors. That means that they're flat. When you have light coming in from a source, it will bounce off of that and come off at the same angle that it came in at, okay? And so that's really important that we understand an angle of incidence, an angle of reflection. Those are these angles up here in the compared to perpendicular position. But the truth is these lower angles up against the glass or against the mirror would be the same as well. They would have the same concept. And so when we look at mirrors, we see some very interesting things. And this is basically what I need you to be able to understand, is how we can draw these ray diagrams. So I'm going to do a really simple example. And then the rest of this is really about your geometry and your basic trigonometry skill set. And so let's take a look at an example with a flat mirror here. There's my mirror. Okay, and let's say that I have I don't know what's an object that we could put in here. Let's say that we have, well, we'll just do a face. Okay. There's your eyes with your mouth. No nose, that's fine. Alright, so our eyes would look straight over. If I wanted to see my eyes, I would look straight at the mirror. Well, that light has to travel from my eyes to the mirror and back. And what that does in the process is makes it look, so there's the actual ray of light, but it makes it look like my face is back here behind the mirror. If you haven't had this experience, go do it, pause the video, go do it right now, and look in the mirror and bring your hand closer to the mirror. You'll notice that it never, until you're right touching the mirror, your hand appears to be sort of behind the wall. That's why we have that. It's almost an optical illusion that we see ourselves smaller, than we really are, because we appear to be further behind. Okay, and so we would see that. Now, the next thing you want to understand is, let's say that I wanted to see my feet. Well, I'll give myself some arms too. My feet aren't inside the mirror size. So you might think, but I can't see because, that's my arms. Well, what we have to remember is that light from our feet would come up, hit the mirror, and bounce off at the same angle that it came in at. So if this angle is the same as that angle, then we would be able to see our feet. But what is that? How does that work with this reflection over here of me that I'm seeing? If we were to follow the straight line path of the light our feet is emitting, right? Instead of doing the bend here, if we were to follow it straight down, we would find a position where our feet would, that's not a very good drawing. Oops. But we would find a position for that same part of our body, just following that. So there's definitely some angles here and some basic trigonometry. With a plane mirror, one of the things you need to understand, this is called the object distance, or DO. And this would be called the image distance, or DI. The object distance and image distance for a flat mirror or a plane mirror are always the same. That's really what you fundamentally need to understand about a flat mirror. And so take it from that approach. Like, understand that's our plane mirrors. But then there are two other types of mirrors that we're going to put a lot of effort into, and it's going to lead the way for what we talk about when we talk about lenses, the lenses that we use to bend light. And so we have, let's say that this is our mirror. Okay, let's say that you put your face right, you're going to stand over here on this side of the mirror. Okay, this would be considered a concave mirror because you can almost see the cave or the concavity, the hole in the mirror. Think of looking at the inside of a spoon. Okay, there's your concave. Then if you flip it around and you show me the back side, this would be considered convex. Okay. Now, a couple things we need to understand about these mirrors. They're going to create very different images depending on how we look at them, depending on how close we get to them. There's a lot of different characteristics that come along with the concave versus convex mirrors. And it's going to be very similar to what happens when we get into lenses, but we do need to talk about some specific rules. Okay. For instance, all of these mirrors, they do have what's called a curvature, a radius of curvature. It's how curved are they. And then they're going to somewhere over here have what's called a focal point. Okay, that would be inside the curve. So this focal point occurs behind the lens, behind the mirror. This one occurs in front of the mirror. Think of if you had straight rays of light, boom. Parallel rays of light, they'd all get brought to that point. It's very similar to how a solar oven works. It's also how reflecting telescopes work, things along those lines. So we have our concave and our convex. A couple of rules. First, we need to understand that the focal length, okay, the point where it focuses, is the radius divided by 2. So that's a formula that we're going to want to understand about all of these, is that our curvature, our radius of curvature divided by 2 is going to give us our focal point. Help us find where that focus is. The other thing that we need to understand is that there's another formula for calculating where it's going to create an image. Because when we look at a mirror, again, there's this point from which we seem to be, the image we're looking at is occurring. So where is the actual image appearing to exist? Sometimes they're real, sometimes they're virtual. We'll talk about that a little bit later, more with lenses. But when we talk about how do we calculate where the image is and things along those lines, I mean, in this problem, the image distance is the object distance. It's just behind the mirror, which creates a virtual image. This isn't a real object back here. We can't really do anything with it. So that's a virtual. But when we talk about these guys, it's a little bit more complicated. We have to use the formula 1 over the distance to the object plus 1 over the distance to the image equals 1 over the focal length. Okay? So there are a couple of rules about what's positive and what's negative. Let's go to the textbook and take a look at some of our rules for sign conventions. Okay? Again, like in a mirror, this image occurs behind the wall. It's not there. You can't actually touch it. You can't actually, like if I put up a piece of paper back here, right here, let's draw our piece of paper. I'm going to put a piece of paper right here. Would that affect what I'm seeing with my eye? Because it's behind, the answer is no. That doesn't actually exist. It just appears to be there. Okay? Some very, very cool questions that you'll get into. You can see this spherical mirror. This is a convex mirror. It allows us to see a larger region of things. A concave mirror is often used for magnification. and we can see this idea of coming to a focal point. But I want to talk a little bit about some ray diagrams right here. I can talk about how we use ray diagrams to determine the physical positioning without doing the calculation. There are 3 rays that we draw, and this is a very simple set of rays to draw. We always go parallel. So this, you guys have to understand, this arrow right here is your object. Maybe that's your face. Maybe that's something else. You take a dot on that, and you're going to slide parallel to the axis, and then bounce off the mirror and come through the focal point. So you can see that's ray number 1. Ray number 2, we take through the focus first. So we're going to go through the focus, but because we came through the focus, when we hit the mirror, we're going to come out parallel to the surface. And you can see this interaction. We can see this is where they're crossing. This must be where the light is gathering. This is where the image would occur. But it's never enough to just say, oh, of course it's going to work out perfectly every time. You should always draw from the tip of the arrow, right, from that high point, through the center to the mirror. Okay, from the mirror through the tip, through the center, will be one straight line. The fact that all 3 lines occur in the exact same spot tells us that is where the image is occurring. So this is an example of a magnification mirror. Okay, and if you look at it, we took something this tall and we made it significantly bigger, and it appears closer to us than it was before. The one issue is it is upside down, which is a little confusing. But if you're not sure about that, get out your spoons and start bring your nose close to it and try looking inside there. See if you can get the images to flip and things along those lines. Okay, but those 3 rays, parallel, then through the focus, then parallel, and straight through the center, are the 3 rays we'll use for ray diagrams over and over again. But we do need to talk about our mirror equation. Right here, there is the magnification equation. It's how much bigger or smaller it's gotten than before. I'll go ahead and write it down with our other formulas. Magnification is just a comparison of the height of the image to the height of the object. If it's a bigger image, then it would have a magnification bigger than 1. Another way to do this is negative di over do. I don't want to mess that up. Let me see. There we go. Negative di over do. That's our other version of the formula. It's going to tell us, are we expecting a bigger object or a smaller object or image when we put something close to a mirror. But there are some sign conventions that we need to talk about. So for sign conventions, if we keep coming down, I don't know if they're going to give it to us in a nice, easy format. Here we go. All right. So our sign conventions. When the object, image, or focal point is on the reflecting side of the mirror, on the left for our drawings, typically we draw them on the left, then the corresponding distance is positive. So for concave, the focal length will be positive. Convex, the focal length will be negative. Sorry, I'm on the wrong screen. There we go. For your sign conventions, concave is always going to be positive focal length, and convex will be a focal length that's negative. If the image is on, we're going to call this the front side of mirror. Okay. DI will be positive. Backside or behind, DI will be negative. And distance to the object is always going to be positive. So DO will be positive for mirrors. There are a few situations when we do combinations of lenses that we could get a negative there, but that will be later towards the end of this chapter. Okay, so at this point, when it comes to making decisions about how to calculate and answer these questions, let's jump down to the textbook and the solutions, or the problems that you need to work on. We're getting there. All right, so these first few questions, they're really just about understanding some stuff. Number 2, you're just going to say that you've done it or that you didn't do it. So you really just need to find a mirror. It doesn't matter how tall it is. Find a mirror and set it up nice and straight, vertical, and walk backwards and forwards. These first 4 are all flat mirrors, and so it's just about basic trigonometry. If you get stuck, just come and ask the questions. Then 23, 7 through 11 are all about creating using spherical mirrors. One thing to keep in mind, I didn't talk about, I did say if it's behind the mirror, it's virtual. If it ever occurs in front of the mirror, then it would be considered real. Although that becomes a very tricky thing in terms of how to actually get that real image to do something. So don't worry too much about that. Remember, concave means it's going to be positive. Convex means it's going to be negative in focal length. You can stay in centimeters on these problems as long as everybody's in the same unit. It's okay. And, you're basically using that 1 over do plus 1 over di equals 1 over f almost the whole time. If you have questions, come see me. But that's it. I think you guys can survive that. And let me know what you need.